and moderator for this seminar, which lasts for 2 days, for today and tomorrow. Yeah, I'm going to be here for 2 days as well, if you allow me to. On behalf of the organizing team from KMUTNB, it is an honor to extend very warm welcome to the esteemed guests, distinguished speakers, and all the participants to this technical seminar titled Bio-based and Textile Reinforced Composites, Design and Development for Large-Scale Production. This seminar is co-organized by King Mongkut University of North Bangkok and the National Science and Technology and Innovation Policy Office, together with the great collaborative support from MERGE, Cluster of Excellence, Germany's first and only federal cluster of excellence in the field of lightweight composites and structures. This seminar aims to offer insightful knowledge and share expertise from the top-level experts in the lightweight structure technology and the application of textile reinforced bio-based composites for automotive, aerospace, civil engineering, and other lightweight structures. This seminar also aims to provide an excellent opportunity for the participants from the industry as well as academics and researchers to learn and get inspired by the invited speakers and somehow can apply this knowledge to their current work and hopefully come up with new ideas or even new innovations. We are very much honored and privileged to have with us in this seminar the very top-notch experts from MERGE, Cluster of Excellence Germany. Okay. To begin with the morning session, I would like to take this opportunity to call on Professor Suchat Sengchin, the Vice President of King Mongkut University of Technology, North Bangkok, to deliver his welcome speech. Please join me in welcome Professor Suchat.
Dear fellows, dear ladies and gentlemen of speaker, good morning everyone. On behalf of the President of King Mongkut University of North Bangkok, Professor Dr. Thilawut Bunyasopon, and management team of the KMUTNB, my name is Suchat Sengchin. I'm the Vice President for Research and Academic Promotion. We would like to warmly welcome you all to the seminar of bio based on textile reinforced composites design development for larger scale production. This could be one of the hot topics of this seminar, which closest to the scale of the production line in the industry. I would like to begin to thank my colleagues at the KMUTNB, especially as it is Professor Dr. Alisala Chaikiti Latana, and the college from Koidem. And also I would like to thank STRI who will support this seminar today, for providing us such a beautiful and impressive seminar. Let me also take this opportunity to thank all guests from abroad, especially from Germany, from two universities, the team of the group of Professor Kohl, which he will join later today, and also Dr. Jürgen Torsch, the leader of this team, and also the team from Professor Wagenfurt from University of Dresden. For grasping our video present today, we are so delighted that you have been taken time from your busy schedule to visit us and present today at the KMUTNB. And I believe that this seminar will offer you all a unique opportunity to share experience and discussing evolving strategy for the space of education, industry, and technology in the field of bio and textile composites. We finally will result in the improvement of the outcome for all research and innovation. Also, we know that King Mongkut University of North Bangkok, we are welcome many visiting academics from overseas every years. And this was an extensive network of education and research institutions at all universities. And such an academic and industry seminar is a major step to forward in promoting and enhancing cooperation in research and development between King Mongkut University of North Bangkok and all of you. Therefore, let us, with a future cooperation in terms of research activity with you all in the near future. And with a good number of participants today, we are sure that this conference will be a memorable, highly educational, and not to be missed event. And we hope that this seminar for bio and textile composites will help you to better understand, to obtain the knowledge in the area of composite technology. And we truly value your participation and support for this seminar. And thank you so much for your coming and your attention. So please enjoy this seminar today, and tomorrow we will continue for the second day. The half day we still have an interesting topic which present by the group from chemists. And I would like to have a good day during your stay in Bangkok, and thanks you all on behalf of the President of King Mongkut University of North Bangkok. Thank you very much, and please enjoy.
Thank you very much, Professor Suchard. Now I would like to take this opportunity for Professor Suchard to give token of appreciations for all the speakers in this seminar. Okay, please.
The Vice President for International Affairs will switch.
Good morning, everyone. So please give me some short time to thank you for all your support. And in the name of Professor Groll, I want to thank Professor Tushar, Professor Arisara for all this really great organization, and not only for this workshop here, but also for all the surrounding events you organized. And since yesterday we already have been on the international conference on engineering innovation, which was a great experience for us. And maybe some of you know already that we are since 2014 every year have been here for more or less 1 week in knowledge transfer, in teaching, education, but also already in research on topics, composites, fiber-reinforced plastics. And then this time we have a really trustful cooperation. So we have already some exchange students in Chemnitz in the research and teaching on fiber-reinforced plastics, and the first results have been presented yesterday on the conference. So this is, I think, really a strong and unique cooperation, and it's an honor for us to be here, and we are really happy that we can make this workshop for you in the next 2 days. And so in the name of Professor Groll, let me thank Professor Tushar for your opening speech, and also for Professor Arisara. So please let us give you some presents from the university.
Thank you. But you have to keep your feeling more. Because you have to work in 2 days more. I will transfer this message to the president. But we will join time by time. Tomorrow, of course, so we have to give you a feeling of being after working after 2 years. Okay, thank you.
Thank you very much. Thank you.
So, ladies and gentlemen, now we are switching from the official stage to the scientific stage here, and it's an honor for me that I can opening this workshop with some introduction on process development for large-scale production and thermoplastic manufacturing processes. So this is as follows organized. We will start with some motivation slides that you get some feeling why I think this is for us an important topic to talk about, and especially not only in Europe but all over the world. It is really a major topic in resource efficiency to avoid emission and carbon dioxide with respect to global warming, all these political megatrends we have. And so we will make some overview. Then we are going on details in the design process. Will grow up, starting from getting some experience how to make a part, which boundary conditions you have to follow in design and development of processes and structures. And then we will go in some deeper insight of fibermetrics, adhesion, calculation, optimization of structures. We will have some insights, especially in the topics of biocomposites, using natural fibers, biopolymers. And we will also go on using fiber-reinforced plastics in civil engineering. And this, I think, you get in more or less 2 days really a lot of content. And therefore, we don't want to make it only talking all the time, present you some information and slides, but it should be also them getting some feedback from you. So we will make some stops between slides. If you have some questions, please don't hesitate, give us a sign, we can stop. Please don't hesitate to ask us if you have some questions on specific slides. Don't wait until the end and maybe you have forgot all your questions. So we really have plenty of time to go through. And you have some handouts, so not all slides on, but most important. And so if you have some more questions to specific slides, to write something down, details, whatever, give us a hand mark, and then we can stop and can answer your questions. So, in the name of Professor Kroll, I would start with some political motivation. So, as I already had mentioned, let me look if it's working. Yeah. First of all, Chemnitz, where we are from. So this is right in the middle of Europe. So Chemnitz is situated there in the border to Poland and Czech Republic. So our university is not so big like KMUTNB. So we have already, let's say, more or less 12,000 students, and the population of the city is, as you can read here, 242,000 people. So, well, should be from the size like a small suburb from Bangkok. So, in the university, we have excellent research in a lot of topics, but especially as it is a technical university, we are focused on faculty of mechanical engineering, of electrical engineering, and natural science. And these are the faculties with some others like mathematics, economics, which are all make the research in our cluster of excellence on merged technologies for multifunctional lightweight structures. So this is a big issue. If you want to create lightweight structures or fiber-reinforced plastics as one special, it's an interdisciplinary subject. You cannot solve the problems alone as normal mechanical engineer. You need a lot of other scientific input. You need engineers, you need mathematics for calculation, you need chemistry, especially polymer chemists for, let's say, optimizing of fibermetrics, adhesion, for example. And so, all to solve this, you need a strong cooperation within the university, but also with cooperation partners, because for us, it's at the university really important to have the feedback of industry, to know what they need, what is necessary for develop application parts for lightweight structures. So you are one of our cooperation partners at the university, one of the strongest partners, especially in Asia. And as I mentioned already, the cooperation with the University of King Mongkut's University was already established in the late 2000s. So we got your Princess, Royal Highness Princess, to Chemnitz, as she has a strong cooperation or belonging to Germany. As I know, she studied already in Germany, not in Chemnitz, unfortunately, but in Aachen, as I know. And we started with the first knowledge transfer in 2014 with a specific lecture on fiber reinforced plastics. And since last year, we, as you can see, it's more or less the same frame. We started in the cooperation and in the teaching natural fiber composites, and we decided last year, okay, we should open it, especially also on textile, not only biocomposites, natural fibers, but on textile fiber reinforced plastics, as there's also a strong demand here in Thailand, in textile industry, to get more insights in technical fibers, technical textiles, and especially application for technical textiles on reinforcement textiles for fiber reinforced plastics or fiber reinforced concrete, for example. So fiber reinforcement is not typical only for fiber reinforced plastics, but it's also reinforcement for concrete, even for ceramics, for metals, and so this is quite interesting to look on. And now we are here on today, and so let's start with this motivation goal. I think it's not only something now politically driven from the government, but also comes from the industry. Most of you, I think, know of our problems we have at the moment with our Volkswagen group, with these problems, how to reduce emission of carbon dioxide. Well, we in Germany say software cannot be a good solution, must be something in hardware, so we have to reduce the weight, for example, of cars to reduce the emission. And by law, we have in Europe in 2020 this regulation that all cars of the whole fleet of automobile group must be below 95 gram carbon dioxide emission per kilometer over the whole fleet. It means smaller cars are already below, but bigger cars are above, and so in the middle, overall, you have to reach this goal. Otherwise, you have to pay for every sold car which is higher. They have to pay a tax to the government. So, of course, the government will be happy because they get a lot of income, but the automobile productions don't want to pay this. And it's not only in Europe, so we also have it in the United States, but also in China. And there's an overall assumption that you can reduce the carbon dioxide emission of 8.5 gram per kilometer if you save a weight of 100 kilogram in the car. So this is one solution to make the cars lighter. Of course, this has to be a combination of also more efficient engines and so on. But to reduce the weight, this is one of the solutions to reach this goal. And the problem is to make lightweight structures is state of the art for aerospace, for aircrafts, for rockets, and so on. But this is really expensive. So no one wants to pay $1 million for a car. So for mass production, you need technologies which enable this lightweight construction, and therefore you cannot use classical production technologies for making classical high-performance fiber reinforced plastics like hand lamination or racing transfer molding to make some thermoset-based carbon fiber reinforced parts. You need technologies especially for thermoplastics like injection molding, press molding, technologies which are suitable for mass production to produce more or less 1,000 cars per day, which is, for example, typical number of production rate for big automobile producers like Toyota, also or Volkswagen and so on. So this is one aim also we have in the cluster. On the one side, we want to reduce the weight of the structures, so we are efficient during the lifetime, but we also need efficient technologies for producing these lightweight structures. So we have to look on two major goals: during lifetime reduction of emission, to be more efficient. This is something natural if you have lightweight structures, and on another side we need efficient technologies. So what we are looking especially is using metal intensive technologies which are based on technology state of the art, like sheet forming, die casting, or for example high pressure forming. And we are looking on textile plastic based technologies, so this is typical fiber reinforced plastics technologies, injection molding for example, and also looking on the integration of micro nano systems in the structures. So today the world is getting more smarter. It means all your structures you have not only in the cars but also applications in civil engineering, medicine. You integrate sensors, sometimes also already actuators in the structures, and therefore if you integrate it with technologies efficiently in the parts, you also can save material. You can be lighter because you don't need additional fasteners for mounting it, and it can be efficient because you don't need additional processing steps. So all these three we are looking on to reach the goal of making lightweight structures. And from the technology view, we are looking on technologies in making semi-finished products, pre-pregs, in technologies which are roll-to-roll, meaning continuous working technologies coming from a roll like a textile. You make something continuous working, functionalization, fiber orientation, impregnation with the matrix, going again on a roll. So this is continuous working. It's not a sequence with some stops between, and then try to go in so-called in situ processes, in mold processes, which means you have a mold where you bring all your components together, and you can use this mold for many parts. Close it, make a part, open it, deform, close it, make a part, open it, demold, and so on, with short cycle times, something between 1 minute, 2 minutes, but not longer. Okay, so to start, how to get something like this solved? We are starting with some basics, how we came from the specifications we get from the industry. You have some supplier who makes some parts for automotive company, and he wants to reduce the weight of some parts because he gets these conditions from the automobile. Normally, some of the automobile companies says, okay, our next generation car must be 200 kilogram in total lighter, and this you have to go to every development area. Under the hood, interior, exterior, everywhere you have to reduce percentage of weight to reach this total amount of, let's say, 200 kilogram for the next generation car. And so you get some boundary conditions, and how to solve this problem. You have to look on the specifications you need, on the design, how to design something with fiber reinforced plastics, and then go from this design to making the mold and making the technology. And this we want to look on in the next, let's say, 1 hour. I have to look a little bit on the timetable. So we have some time to go step by step, and for example, I have a part with me where we can look how to develop it step by step. Okay, so for the design approach, starting with this. And normally, automobile production today is nothing which you start by the scratch. You have already some car, and to looking on the design, there are more or less two typical ways how to make it in the design process to reach or to get such a lightweight, let's say, lightweight car. On the left side, it's the typical called revolutionary design. So you start with nothing, and you have the possibility to make car body, for example, totally new without any boundary conditions from an old car you have already. So you have the possibility to make a load-adapted design. So you can make the construction that all your fibers are aligned as your load is. You can make your fibers in direction of the force, because this is something you get later perpendicular to fibers you don't have any reinforcement effect. So this is something lightweight designers love, but unfortunately it's not the typical way, because more or less, as I mentioned already, you have a car already, and so you have to make it like seen on the right side, an evolutionary design. So you have a car, and step by step you replace some single structures which are still in steel in the old version, and you try to redesign it on fiber reinforced plastics, for example. So this is not so easy, because then you have some boundary conditions already given, and you have the design frame and the space you can use for your design of new fiber reinforced plastic parts, which are restricted on the design of the old steel-made part. So this is not so easy, because to design in steel is totally different when you want to design in fiber reinforced plastics. But unfortunately, this is the typical way, evolutionary, step by step, make the car lighter, starting with this part and the next part and so on. So when we are looking, for example, at Volkswagen, the new Golf is the typical small car. You sell mostly 1 million cars per year, or not so much, but let's say 500,000. You slowly, step by step, reduce the weight by making some parts change from die casting to sheet metal, going from sheet metal design to fiber reinforced plastics, or to injection molding, something like this, step by step. So you don't design it totally in fiber reinforced plastics. You have still some parts in steel, you have still some parts in total plastic, some parts in fiber reinforced plastics, which then you have such an hybrid metal fiber reinforced construction. And for example, some revolutionary design, maybe you have heard of the BMW i3, which is totally made new, made from with a car body made from carbon fibers. This is more or less revolutionary design. It looks like a normal car. So the classical car body is like a steel car, but inside the whole car body is made from carbon fiber reinforced plastics. And the design is still not so optimized load adapted. So you have a lot of waste in fibers which you cannot use for load transfer, load introduction, but it's some solution between these both. And the normal cars, like from Volkswagen, you start with a evolutionary design. So in the revolutionary design, you have the possibility to make some topology optimized construction, that you have construction with, let's say, stiffeners, ribs, profiles made from carbon fiber reinforced plastics. The load transfer is only here, so this is really, you have material only there where you need it. Yeah? And it's fiber-friendly load transfer, so the load goes only in fiber direction. in the evolutionary design, as you can see here, for example, like such a pillar for the roof reinforcement, you change single components, make them from, let's say here, from fibers at the end. For the assembly, you have some steel-made parts, and you have to assemble it with the normal steel car body. And you step by step change some parts, and you need then, of course, assembly technologies, fasteners or gluing or welding, something like this, where you can join the fiber-reinforced plastic parts with the normal steel. So that's not so easy, especially if you use carbon fibers. You have problems with corrosion if you have directly contact between carbon fibers and, let's say, steel or aluminum. So you have to look on quite interesting joining techniques. This is something, for example, Sascha Müller will discuss on some joining techniques later on, how to solve such problems. Now, the next is design approach, how to reach lightweight design. So you have more or less 3 major topics to reduce the weight. The one, I think this is the most easy to understand, using lightweight materials. So per definition, lightweight is something with a density below, let's say, 5 gram per cubic centimeter. So per definition, aluminum is a lightweight material, titanium is a lightweight material, magnesium is a lightweight material, but also, of course, plastic and fiber-reinforced plastics. Yeah, so because the density is below 5 gram per cubic centimeter, so with normal plastics we are around 1, depends if it swim on the water or not, so this is easy to look on. With some fibers in, a glass fiber has a density of, let's say, 2.7, so in the combination with plastics we are in the density of, let's say, 1.4, 1.5 gram per square cubic centimeter. So this is something easily to understand. But of course, lightweight you can also make with a construction with steel. Yeah? Let's say a bridge construction. So steel with a density of 7 is not a lightweight material, but in the construction, for example, let's say rib structures, sandwich structures, this is something you can reach lightweight design because of the, or you can reduce the weight only with the design. So, for example, Dr. Sandra Gelbrich, tomorrow we speak on also on fiber-reinforced concrete. So also this is something you can construct with concrete and a lightweight design. So this is a topic of the construction. And last but not least, to reach lightweight design is something you can make by integration of functions in one part which you made before with separate parts, for example, having some kinetics, you have some fiber-reinforced plastic, and you want, for example, a seat in a car, you want move for your seat in the high or in the for your back to reach some position. You can reach it with some additional mounting parts like an electric motor, you need some electric devices, but with some tricky design of fiber-reinforced plastics, you can reach this goal also without an electricity part, without an motor, without an electric drive, and so you can reduce the weight. Because in all electric applications you have copper, which is really heavy material, you have steel inside, so you can reduce the weight. Also, if you have some sensors integrated, you can avoid some devices for switch on, switch off. You can reduce also the weight and so on. So on this we are looking, materials, structures and integration of function and systems to reach a lightweight design. And for today in all the system, we are concentrating at the moment in the lightweight materials on fiber-reinforced plastics. for the next 2 days. And so, having this in mind, lightweight is not only made with fiber reinforced plastics, it's a quite interesting part, but you also can deal with lightweight metals and so on. And in this combination, together with lightweight structures, we call lightweight systems. There we can reach really a goal of reduced weight, let's say 20-30%, to use lightweight materials, and with a really tough and smart design to get lightweight also in the application. Now, lightweight, to reduce the weight, this is not something you can get cheap. It needs some efforts in using materials, new technologies, and also, of course, in engineering costs. Because, well, design with metal, it's also tricky, but it's even more tricky to engineer fiber reinforced plastics, because the material behavior is not isotropic, it's anisotropic. So you have different material properties in different directions because of the fiber orientation. So in steel, the tensile modulus is in every direction more or less the same. For fiber reinforced plastics, it is not so. And so for designing, it's really something you see here in the green. Your engineering costs will really rapidly increase if you want to reach really lightweight application. Of course, when you can save weight, more or less you can also reduce your poor material cost if you don't need so much material, but your specific material costs will rapidly increase because carbon fibers are much more expensive, let's say, in compared to steel. So in total, also your manufacturing costs will increase because you need new technologies. Total costs will rapidly increase when you want to increase the lightweight degree. So designing something which have to fly, like aircrafts or rockets, it's really expensive. For mass application, no one wants to pay so much money for a car. He don't have to fly, he only has to go on the street. You want to reduce the emission. So you need some optimized zone of lightweight design where you have an more or less optimizing of all your influences which influence your total costs, not to make such a huge lightweight degree which needs a lot of engineering time, and engineering means personnel costs especially. You need something here where you have an optimization of all this. Now, this is something looking on the costs, part per weight. So of course, you can save the weight, but you increase your material costs. So, which is here related to steel, which is here, let's say, 100% of the costs. So, here the weight, sorry, here the costs. So, looking from steel, high-strength steel, you can already reduce the weight, but your costs will slightly increase. With plastics, you can, compared to steel, reduce the weight, but you're more or less on the same price level. With aluminum, you can much more reduce the weight, but you will already increase the cost because of the material. Aluminum is much more expensive. And with carbon fibers, you can, let's say, save weight of 50%, but it's cut it here. Your cost will be, let's say, 6 times higher, only because of the carbon fibers. So you always have to look how much weight you can save, but how much will your production costs increase, and therefore not only production costs, only in application your part costs, which you have to sell. Yeah? And no one only will buy a car, it's light, with the green thinking, but have to pay 5 times more than a normal car. So no one is so idealistic only for green thinking to reduce the weight to pay so much money for a car. Yeah? And So this is our problem we have. And to solve this, you have to look on many things. Of course, we need much more costs reduced in the carbon fibers, but also in the production costs. And this is something, problem of, let's say, we call it the problem between chicken and egg, because carbon fibers are expensive. Because they are so expensive, no one buys them. More or less, only producers of aircraft like Boeing and Airbus buy all these fibers. And so the market is not so big, and therefore you cannot reduce the price of different carbon fibers. If more people would buy carbon fibers, you would have a reduction of the carbon fiber cost, because you are more efficient. You can produce more with bigger amount, with bigger technical devices, but this is a problem. Selling the fibers, as more you can sell, as cheaper you get the fibers, but they are still too expensive. So the automobile production don't want to buy it. So this is something the market slightly increases with producing of fibers, and so the carbon fiber price only slightly decreases. So we have to wait to make more developments, efficient developments in fiber reinforced plastics, and therefore we can get more application for fiber reinforced plastics. The producers of carbon fibers can reduce the price, and so it will be much more increase. Yeah? And so this is some foresight studies. So at the market, we have, let's say, 3 to 4 or 5 global producers of carbon fibers, and they are sharing the market. And there are some foresight studies how the price for carbon fibers will reduce in the next years, but it depends on the application. As more application we have, as more the price for carbon fibers can reduce. It will not be never so cheap like glass fibers, because it comes from the precursor. It means the basic material you need for carbon fibers. But of course, we have some foresights that it will be reduced, let's say, up to 50% in the next, let's say, almost 15 years, 20 years. Okay, so this for the introduction. Now I want to show one part where we want to go step by step through how we come to the fiber reinforced plastic part. Okay, so this is, let's say, a typical demonstrator we are making the research on. It's at the moment a normal plastic part. It's injection molded part without any fibers inside. Injection molded, you have the gates for the plastic melt here. We have some honeycomb stiffener structure behind. And step by step, Isabel can show me. Step by step, we want to integrate some textile reinforcement in, so that we at the end, let's say, reach. This here. That we at the end reach the textile fiber reinforced part. Yeah. So this is something, let's say, one customer wants to have, and so we go through step by step how to reach this. Okay. Okay, at the first step, I will give you the poor plastic part that you see it how it is. So, as you can see on the on the right side, this is our part. Now, let's say it's some roof element, whatever. It's a demonstrator for us for the technologies. We have a boundary condition that we have some load from the side. So when you look on the part at the edges here, you have some holes inside where you can then mount it on another part. And so we have some boundary condition. We need load from the side to bend it in this case. And now to make something like this, we can make it in plastics. So we know our mechanical properties we have, let's say tensile modulus, tensile strength. We know some impact properties from the pure plastic. In this case, it's in polypropylene, but it's not enough. We need some strengthening of the part to get a higher stiffness and higher strength. So first is, as I mentioned already, fibers for the reinforcement have a reinforcement effect only in fiber direction. So it's not an isotropic material, it's an anisotropic materials. And as we know from steel, we have one tensile modulus, we have one shear modulus, and depend on the kind of steel, we have different in the strengths. But in all directions, the same strength. So typical for steel, we have only one tensile modulus. So tensile modulus for steel, all should more or less know. We have 210 gigapascal tensile modulus. For the strength, it depends on the sort of steel. Let's say 350 MPa for normal stainless steel, can be higher, up to 1000 megapascal for high strength steels, but that's it. Now, for our fiber reinforced plastics, as you can see here, let's say we have some, which is black, made here, the fibers, single carbon fibers embedded in some yellow matrix. We have one tensile modulus in fiber direction. We have another tensile modulus perpendicular to fiber direction. And here we have one shear modulus. Also we have two different Poisson ratio. So nothing I want to go too much in details, but especially tensile modulus in fiber direction and tensile modulus perpendicular to fiber direction is totally different. And this is only for calculation. I think it's clear if you have, like here, a carbon fiber with a really high tensile modulus. It's really stiff, and we have some weak matrix. The weak matrix, like polypropylene, we have a really, really low stiffness. So this is like if you have a parallel connection of a stiff fiber and a weak fiber, from a stiff spring and from a weak spring. Okay. Now, if you give some force on it, some load, more or less, the stiff spring, the stiff fiber will take all the load, and the weak matrix will go with. So we have the same elongation, but the sharing of the force is totally different. So stiff fiber will take more or less all of the load, the weak not so much, the weak matrix not so much. And therefore your calculation of the total resulting stiffness, so the tensile modulus is something related to the tensile modulus of the fiber, relating to the fiber content. I think it's clear. If you have more or less no fibers inside, the tensile modulus will be something of the matrix. If you have more or less only fibers, the tensile modulus will be tensile modulus of the fibers. So that's related. And now, if you all look in the composite fiber reinforced plastic perpendicular to fiber, it's something like a series connection of a stiff spring of the fiber and the matrix. And so the load is more or less the same, going through all. So also the matrix has to take the same load as the fiber, and therefore you can, I think, imagine that there's a big difference if you have a load in fiber direction or perpendicular to it. Okay? So the resulting tensile modulus is something totally different in the calculation to this tensile modulus of the fiber reinforced plastics in fiber direction. And as an example, you see it here. So this is something, a typical carbon fiber reinforced composite material, all fibers in one direction, so-called unidirectional layer. And you have here all the material parameters you need. So you see how many it are in compared to steel. For steel you have one tensile modulus, for steel you have one shear modulus, more or less one strength, and one Poisson ratio. For here, let's say this is a typical composite made from epoxy, thermoset matrix, a STRI, carbon fiber with a fiber volume ratio of 60%. And now you see the tensile modulus in fiber direction and perpendicular. So this is a huge difference. You have more or less no stiffness perpendicular to the fibers, a huge stiffness in fiber direction. Okay? So designing with fiber reinforced plastics, it depends. You have a lot of variations where you can adapt your specifications from the material on the load. First is the fiber volume content, which fiber you use, which matrix you are using, and then you have all this resulting different properties. So this makes it so difficult in the engineering, yeah? So engineering, calculation, design with fiber reinforced plastics is much more complicated than design with, let's say, classical steel. So now, if you have some single fiber, that's quite nice to have, but with a single fiber you cannot make any part. So the first is you have some boundary conditions. Let's say we have the part, what I showed before, and the part that's going through, and we know we want to integrate some reinforcements inside. You cannot take a single fiber, as a single fiber has a micrometer and diameter from, let's say, 14 micrometers. You cannot handle some single fiber. You always have to make some textile fabric from the fibers. So your boundary conditions for the part, especially for the reinforcement effect, say depend on the design of your textile, because with the design of your textile fabric you can adapt your fiber volume content, your fiber orientation, your thickness of your laminate, and so on. But you always have to keep in mind the reinforcement effect only is in fiber direction, not perpendicular to it. So this is something, first is you have to look what are your loads you want to apply on your part, which fiber length you need. So it's easier to make a, let's say, thermoplastic process with short fibers instead of endless fibers. And so you have to look if it is necessary to use endless fibers, long fibers, or maybe it's already sufficient to use short fibers. Because in a part, you can see it here, your properties of course depend on your fiber volume content, but also on your fiber length. But this is something related what of your mechanical properties you are focused on. So especially the stiffness, which means the tensile modulus, already reaches a good level with short fibers. Yeah? So if you only want to increase the stiffness of your part, sometimes it's not necessary to have long fibers. Sometimes it's totally sufficient to use short fibers. This depends on your so-called critical fiber length, which normally in the part is something related. So length of the fiber divided by the diameter of the fiber should be something around 1,000, 2,000, 3,000. This is totally sufficient for the fiber length in a part, if you look especially on the stiffness. So as you can see here, related properties, you reach already a nice level if you have a fiber length, let's say of 1 millimeter for, let's say, thermoplastic parts injection molding. Yeah? So longer fiber sometimes not necessary if you look on stiffness. Of course, your strength, then it makes sense to have a little bit longer fibers in the relation between 1 to 10 millimeters. Most increase in increasing the fiber length, you get better properties in the impact. So crash, energy absorption. So yeah, it's totally necessary to have long fibers. Okay, so as you can see here, depend on if you use, for example, glass fibers or carbon fibers. It's quite interesting. The critical fiber length is 3.3 millimeters for this application. For glass fibers, 1.5 millimeters for carbon fiber. So this is something you can reach with compression molding, bulk molding, injection molding, more or less. You don't need some really textile reinforcement with endless fibers. So, for example, you see it here a nice research we made on. This is something we compared polypropylene injection molded parts with glass fibers. You see here short glass fiber. We made the abbreviation short glass fiber SGF, and endless fibers. We had a multi-directional non-crimp fabric, endless fibers NCF. Of course, with short glass fiber injection molding, you more or less reach only a fiber volume content of 35% volume. More is more or less not possible of the technology of injection molding and compounding. With a textile reinforcement, you integrate some non-crimp fabric directly into the mold with 4 fiber layers, 0 and 90 degrees mixed. We reach, of course, higher fiber volume content of 48%, but if you when you compare now the resulting properties in the part, you see short glass fiber, we are something on this level, non-crimp fibers, we are on this level, so the difference is not so much, yeah, in the stiffness. Because already with short fibers, we reach quite a good level. When we are looking on the tensile strength, it's already another a bigger difference. Yeah, you see it here. Let's say something between 30-35% in compared to the non-crimp fabric. The tensile strength strain already increases, but the most difference you see in the impact properties. Yeah? Because with short fibers, if you have some crash, the fibers will be pulled out of the matrix. It depends also on your fiber matrix adhesion. But as longer the fibers, as more energy absorption you have in the friction between fiber pull out and matrix, you reach really only 1/20 of the properties short fiber in compared to endless fibers. Okay? So depends on the boundary conditions you get from your applier, which you want to have as increase of your properties in the part. If you are focusing on stiffness, then sometimes it makes sense only use short fibers because this is more easier process in making the part. If you are looking on impact, on strength, then it makes sense to make endless fibers, but related to stiffness, you maybe also be already sufficient with short fibers. So now, when you have the decision what fibers you want to use, short fibers or endless fibers, you have a big problem. You have a huge variety of process routes you can reach the goal. Yeah? So you have a fiber, you have a matrix, you want to reach a final part. And now between, you have plenty of possibilities how to reach this goal. So, and you always have to look which fibers, which textile process, which matrix, what combination you use. Yeah? So, for example, take a single fiber, you go to the roving. This is what you can normally buy from a fiber supplier, carbon fiber roving. You have some text, you have some typical tider. You can use directly the roving for, let's say, fiber spraying, pultrusion, filament binding. You have to combine it with the matrix. You have different ways. Normally, wet impregnation means you have your resin or a thermoplastic melt. you can directly go over filament winding into impregnation, you have your part. But of course, you also can make it with the fiber going to a textile process. You make some textile fabric. Let's say you can go to weaving, you can go to laying process, make some non-crimped fabrics. You have your textile. Then additional, you have to impregnate it. You have to combine this with the matrix. You have some different possibilities. Directly take your textile fabric, combine it with the melt, make the impregnation go to the part, or you also have the possibility to make your matrix to a non-woven. Yes? A spoon lid, some matrix, you can make it in a foil, so you can then go to the impregnation. So wow, you have a huge variety of possibilities, and to look what is the best for your product, you have not a rule. You can say for this you need this. This is always depends on your geometry, on your matrix you want to use, on your technical invest you want to make, on the amount of parts you want to do. So keeping in mind, there is no solution for all. There are a lot of solutions to depend according to the technology to use your final product. And you have to look on all this, not single. You cannot look on the geometry design independent of the technology, because not all geometries you can realize by all technologies. And so this all you have to look together. Okay, so coming from the single fiber, going to one-dimensional textiles like rovings. This is what you buy normally from the supplier, carbon fiber rovings, glass fiber rovings. You can use them as they are for filament winding, for example, for making rotational symmetric parts like vessels, tanks, and so on. Or even for open mold process like fiber spraying, you have your roving. You go with a fiber spraying system, directly making some big parts like housing of a swimming pool or the body of some boats. This is typical fiber spraying technologies for using rovings. But normally you take the rovings, and this is something especially the textile producers of textile machines looking on how to make two-dimensional products which are suitable for the resulting part. So most common are woven fabrics, non-crimped fabrics, non-woven, but of course you also can make knitted, warp knitted fabrics, but this is something really specialized. You have to look on the application. And not so often three-dimensional, like 3D woven, you can make braided preforms, or let's say spacer fabrics, like warp knitted spacer fabrics. So, from our point of view, what are the most important, we think, suitable for using for mass production of thermoplastic materials? Now, woven, I think it's clear. You have many varieties how you can your weave style. The normal plane, as you can see here, you have a lot of crimp, meaning your fibers are not going in one direction because of the weaving process. You are going up and down, and always remember on the basics, fiber reinforcement effect is only in fiber direction. Now, as you can see here the fiber direction is in this direction, going around, your fiber direction goes there, going down. So you don't have such an efficient fiber using of the fibers, because your fiber direction is not only in plane, but it also goes in thickness. So woven fabrics are easy to handle, but because of the crimp, your stiffness of the laminate is not so good as if you have unidirectional fibers. As lower your float is, as better is also your drapability. So if you have huge, complex geometries and your part is shaped, it's better to have a high float, not so big crimp, then it's easier to drape. Yeah? instead of this, you also can use non-crimp fabrics. So, for example, looking on fiber woven fabrics, you can reach high fiber volume content. It's more or less inexpensive, have a good stability, but you have not so good traceability, and your fiber orientation is restricted. Weaving more or less only works in fiber direction, so 0 degree and 90 degree. You cannot weave 15 degree, 30 degree, 60 degree. Yeah? That's the problem. And as you have a high fiber volume content, it's not easy to impregnate with the matrix. So you need your matrix inside of the fibers to reach this reinforcement effect. Therefore, we more like to use non-crimp fabrics, especially for thermoplastic application. Why this is so, we will get later, but with thermoplastic melts, impregnation is much more complicated because they are not so easy in flow. Thermoplastic melts have really high viscosity, so the fluidity is really low instead of thermoset resins. And if you look on non-crimp fabrics, as you can see here, you can adapt your fiber volume content, and also you can adapt your fiber orientation. So it's easier for laying process. You normally go on multi-axial machines. You have some stitching process for fixation your fiber rovings inside of the non-crimp fabric, and you can lay your rovings in different directions, and this is more efficient for producing load adapted fiber reinforced plastic structures, because you can adapt your fiber orientation more on how the force flow is inside of the part instead of weaving, because in weaving you always have in the basic layer 0 degree at 90 degree. So non-crimp fabrics from our view for thermoplastic application are much more interesting. They have a very good drape. You can highly align your fibers because you have no crimp like in weaving. So you are laying more or less aligned in fiber direction, in direction and in plane. You have much more flexible fiber orientation, and of course this is some disadvantage as you have more variety in the area of density. You cannot reach the yarn counts as in weaving. You are normally a little bit lower in the fiber volume content. But more or less, we have more advantages in compared to weaving products than disadvantages. So, looking on the summarizing, non-woven, knitted fabrics, non-crimps and woven fabrics. Stiffness and strength we reach already with non-crimp fabrics are really a good level, but the drape properties are much more better than in compared to woven, and the cost and technological expenditure is much more higher for woven. Non-crimp fabrics, it starts already in compared to non-woven. So non-woven is easy to make, but the fiber volume content and the fiber orientation is not so that it reach a good strength and stiffness. Okay. So this is when we have looked on the textile. Till now we have some questions on textiles. Maybe we can.
What kind of fabric that can be used for using non-crimp fabric? You have limitation on that to use a non-crimp techniques.
For the fibers?
For the fibers, yes.
More or less no. So okay. Normally you can use glass fibers, carbon fibers, aramid, so Kevlar, aramid fibers. It's not a problem. Also natural fibers. So normally you can say with all technical textiles, technologies like weaving, laying, you can use more or less all technical fibers. So it's only you have some, of course, some small difference in some mechanical parts from guiding the fibers, because the friction is a little bit different compared to normal clothing like cotton fibers. And the only thing you have really to ensure is when you handle carbon fibers, as carbon fibers are electrical conductive, you have to ensure that they don't get access to your control unit. So this is something, big problem using carbon fibers because of the electric conductivity. If you process carbon fibers, you get some fiber flying around, some small broken fibers. They should not go on your control unit, because if you get some contact, you get some electrical error, and it's destroyed more or less. So this is something you have to ensure.
Okay, thank you.
Professor, I would like to ask a question on the page number 8.
No, oh, sorry. This one? 8?
I would like to ask you about the carbon fiber. You explained the cost of the carbon fiber made by pan precursor.
So you mean which slide you mean?
Yes, the question.
7. Ah,
8. Yes, compare between the carbon fiber made by pan precursor and lignin-based precursor. You have already have a know-how to produce the carbon fiber by lignin-based?
Lignin-based. So at our institute we don't have any experience, but I know that there is a big issue to make research on lignin-based precursor for carbon fibers. As I know at the moment, the problem is lignin is more or less not so easy to handle like in the pen process, and especially in the amount of carbon you get out of in the carbonization process. It's not so easy to handle, because you need when you, for example, come from the pan fiber, so the polyacryl nitrile fiber, your amount of getting carbon out of it is much more better, and also the related properties, stiffness and strength, are still higher. So I know from some research institutes in Germany looking on development of producing carbon fiber from lignin, but at the moment it's still in research, and they don't reach the properties of the, let's say, synthetic artificial fibers, and even the process is still slower. Lignin is much more cheaper, of course, but problem, as I know, you have the pen fiber, pitch fiber, and the lignin fiber, you're much more lower still now in the properties. Yeah. So I know from 2 research institutes in Germany making the research on lignin fibers. It's one is the Fraunhofer Institute for Applied Polymer Science, IAP in Potsdam, in the near of Potsdam, and one is the Fraunhofer Institute for Chemical Technologies, ICT. It's in the near of Stuttgart. They are both on research, but at the moment it's not. I think it needs some years to go on the market. So maybe.
Okay. Next question is on page 16. 16.
Mr. Okay. 16. Yeah.
My question is, in the
Left on the left side.
yes, in the graph, your vertical line is property. I would like to know the unit of the stiffness and strength in back and leg. The same unit or not?
No, it's related to one, means one is 100% of the level you can reach for each of these properties. So depending on the fiber length, the highest level you can reach in the properties is related to 1. It's normalized. Yeah, it's normalized only to show the quality of the level you can reach.
In this case, the fiber which have a length of fiber is optimizing about, at your comment, more than 10 millimeter. So in case of we use the short fiber for the natural fiber, if we cut the length of the fiber, which one is the best one for use for the composites?
This depends. You have to look also on the diameter and of the properties of the fiber and also of the fiber matrix adhesion. So this is something, if you have a perfect adhesion between the fiber and the matrix, and you know, for example, it depends on the critical fiber length depends on the relation between stiffness and strength of the fiber, specific related to the fiber diameter. So let's say as smaller the stiffness of the fiber is, and as bigger the fiber diameter is, as shorter is the critical fiber length. So yeah, must be so, because the load transfer from the matrix the load transfer into the fiber came from the matrix. So with the matrix, you realize the introduction of the load from the part into the fibers, and at some point you introduce the matrix, the load along the surface of the fiber into the fiber. In some case, you introduce so much fibers that the fiber reach their specific strength or stiffness and get a break within the matrix. And so you cannot see it, you cannot say it for all fibers. You have to look specific on the fiber. Especially for natural fibers, there will be a big difference in the critical fiber length. So which you named the fiber you want to use. What was the fiber?
If I use for the hemp fiber.
Hemp. Okay.
In this case, we have a long fiber about 1 meter, 100 millimeter. We should cut the optimum length to make the composite. So which length is more suitable for make the composite, for making plastic composites?
So from my point of view, it should be much more longer than for glass and carbon fibers, as I think carbon matrix adhesion will not be so good, and also to introduce the load. But this is something you have to look on experimental. You cannot say it from here, because you have to look what is the stiffness of the fiber. You have to test it. I don't know what is the mechanical property of the single hemp fiber, and then you can look on. But I will say it should be something. For example, injection molding, it makes not sense to make it longer than, let's say, 20-30 millimeter. It will be shorter. Related here, when you're much looking especially on the stiffness. For the strength, might be longer, of course, especially for the load introduction. But yeah, this is something you cannot, you have to test it. It's easy to test because make some different fiber lengths of your fiber. If you cannot cut specific, you should test it.
I read from some paper. He said the natural fiber length for made composite is 30 millimeter is the best one. So I think from this graph I can estimation your optimum strength will be after the number 3. It should be more than about nearly 1,000 millimeter.
Yeah, it's here it's in the logarithmic scale, as you can see. So might be there was a publication on 30 millimeters for the hemp fiber, or yeah.
So shall we go for a short break and then we continue for the talk of Dr. Okay, thank you very much. Yeah. So we're going for a short break now, and we're going to continue for the rest of Dr. Jürgen Drosch's talk. Yeah. So let's say 20 minutes. Okay, we have a short break for 20 minutes, and we come back again. Okay, thank you.
Jetzt muss ich mal gucken. So I have to look. I'm now.